Terrific. So our featured speaker today is Vladimir Bulatov, who began his career as a theoretical physicist, focusing on quantum mechanical problems related to the electronic structure of crystals. Throughout his career, he has been passionate about computer visualization of physical phenomena, and for the last 12 years of his professional life, he worked at Shapeways, developing algorithms for 3D printing. Now retired, he devotes his time to various software and artistic projects, including SimHub and the MC Escher Infinity Room. He also won the Best Sculpture, Textile, or Other Medium category at the 2024 Joint Math Meetings Art Show and has been an active member of in our community. So I'm really, really excited to hear from Vladimir today. Take it away.
Okay, thank you. So, either I'm doing symmetry work for our first thing I did it was like a virtual kaleidoscope in VRML in 1997, and since then I cannot stop doing it. And mostly I'm kind of inspired by like pure beauty, but from time to time I'm kind of stumbling on some interesting mathematical or physical phenomena doing this. So it is outline of my talk. I will speak about like what is symmetry, shapes, and transformations. Start with traditional method to create symmetries and few examples made this using this traditional method. And after that, I describe efficient modern method of creating symmetries called inverse pixel mapping. And after that, we'll advertise our project, which I am working with, called SimHub, and several applications of SimHub. It is SimPix, it is symmetry from pictures, SimChaos, symmetry from chaotic attractors, SimSim, symmetries from computer simulations. And we'll finish with SimHub to-do list. Basically, it is open source project, and everybody is welcome to join. So what is symmetry? We recognize symmetry when we see it. It is, we recognize it kind of even if it's not perfect. There's like some rotation, but it is not exact rotation, but still it is mostly it is beautiful, something like our eye can recognize these beautiful things. Let's go, what does Google say about what is symmetry? A little bit like naive definition, symmetry property where something is exactly the same on both sides of dividing line, plane, or axis. And it is balance of repetition of parts in a shape, object, or pattern. And the most common types of reflection symmetry where one half is a mirror image of other, and rotational symmetry where shape looks the same after being turned. Another definition, it is crystallography definition. It is, was written in a book by Shubnikov. By symmetrical figure, we means in the broader sense a figure made of equal and uniformly spaced components. As we can see, the concept of symmetry has been assembled from concept of figure, the equality of figures, and the uniformity of their spacing. It is clear that the study of symmetry will have a different content depending upon the meaning of this basic concept. I like this definition more, like it actually saying that there's a spacing, figure, equality, and the meaning of this figure, spacing, and equality is actually not defined. We can put different meaning. So let's start with a simple figure, letter R with no symmetry, and let's add transformations to reflection plane, and either one figure or two figure. So we look like this, like it is single figure, maybe having two components, but another example is symmetry. It is clearly looks like a one figure, and it has like reflection symmetry at the center. Another example of rotation symmetry, large example of symmetry is rotation around point by 180 degrees. Another one, and interesting, like any rotation, so this rotation by 180 degrees is can be represented as a combination of reflections in two axes, in two planes orthogonal to each other, forming a 90-degree angle. And in case of rotation by 120 degrees, it is different single figure. It is again rotation by 120 degrees can be represented as reflections in two planes forming angle 60 degrees. Another transformation is translation, and translation by vector A can be represented as a reflection in two parallel planes, distance A over 2. And interesting, more difficult transformation is glide reflections. It is interesting. I kind of did show glide reflection with like this curvy error, because it is glide reflection. It is not necessary kind of always have visible line of reflection. It is combination of translation and reflection, but somehow this reflection line is kind of hidden in the image usually. And this glide reflection can be represented as a sequence of 3 reflections, reflection in 2 parallel planes, and 1 plane orthogonal to them. And we can combine all these elements in arbitrary order and create an image which is kind of, here it is hard to recognize what kind of symmetries points are, what elements forming this figure. And I marked these elements. It is 2 different kind of second order symmetry, second order axis, green and blue, and this glide reflection with a marked with a dotted line. We want to add to this set of transformation with another one, which is called inversion in a circle or sphere. It is, first of all, it looks like it is something like very odd transformation, but in reality, it looks very much like reflection when we increasing the radius of this circle. So combination of 2 reflections in 2 circles, 2 concentric circles, it actually a scaling transform. We can see these are kind of double reflections. It repeat its shape completely identical with like usual Euclidean scaling. And if we will do this combination of reflections in 2 non-concentric circles, but which don't intersect, we have transformation we called hyperbolic transformation, and it is has like 2 fixed points, so like the shapes going from one fixed point to another fixed point, getting from like a very small size and getting again into very small size. Another variant, when we have a combination of reflections in 2 non-concentric with 2 intersecting circles, it is called elliptic transformation. It is very similar to rotation around point when these circles became of infinite radius. So this combination of reflections in circles and line, they actually, like all the set transformations, they form a complete, they describe transformation of inverse with geometry. So our complete set of transformation are composition of reflections and planes in inversion of sphere. This plane, because plane is kind of limit of a sphere, we will call both plane and sphere as a single word, splane. It was invented by Wilker in his paper Inversive Geometry. and inversion in both a sphere and reflection in a plane we can call also by a single term reflection in a plane. This is actually like I would say a very definite introduction into inversive geometry by Wilker 1982. It is accessible to non-hardcore mathematician, and at the same time it has all kind of correct idea to start to work it. We can say that three-dimensional inversive geometry is actually geometry of four-dimensional hyperbolic space, geometry on infinity of hyperbolic space. It is, we can say like they are like model of hyperbolic geometry, upper half plane, upper half space, which have in this case of upper half space, it is three-dimensional hyperbolic geometry. We have a plane and half space above this plane is the place where the geometry, hyperbolic geometry can be represented. And for three dimensions, our three-dimensional space is like a boundary of this four-dimensional hyperbolic geometry. And we can use inversive geometry as a like container for both for all Euclidean, hyperbolic, and spherical geometry. One kind of troubles of hyperbolic inversive geometry is that there is no solid motion of distance between points. We cannot like define distance which is invariant when we under transformations. So now let's start to do how we can define symmetry using the shapes. It is like simple approach which I used quite a while, and everybody was doing this. It is we have original shape on the right, and we can usually this shape is defined as a set of like control points, like maybe it is a spline, maybe it is a set of straight line and spheres, and we can apply transformation from our inversive geometry. In this case, it is translation, or in this case, it is reflection. We can apply this transformation to each of control point, which I marked these control points, and after that, draw new shape with new control points, and we have transformed shape. But it is, I would say, it is natural way, and it is doable, and potentially it has ability when you doing like physical model, you have no other choice except basically like you take your original shape, move it inside of like your three-dimensional space and glue them together. It is like wooden pieces. It consists of 60 identical segments of wood, and each segment had to be made independently and basically assembled in a three-dimensional space. Another example I was doing for a while is 3D printed metal sculptures. So basically, it is what it consists of 60, or not 60 in this case, it is 30 like pieces like this. It is segment of like twisted band, which are intersected and connected together, but it was done by actually modeling one piece, and after that moving in space according to icosahedral symmetry group, and doing all the intersection, and after that sending to manufacturing. It is another set of examples. It is printed bracelet, and it started to show. I was trying to do like hyperbolic bracelet with hyperbolic pattern, and they already started to show like troubles of like this direct approach. You see there like this solid metal band around on the boundary of these bracelets, and you can say that, okay, it is like part of design, but in reality, it is here also for practical reasons. The hyperbolic structure on the boundaries of this bracelet, because so small, it is kind of it is like zero size on the boundary. How you make something of zero size in the physical model, and this another one is like also made by this direct approach, kind of multiplying pieces in space, and this like the boundary along these shapes, it is really making very small and sharp, and it was very hard to actually to design. And another example, it is really, in this example, it is three-dimensional or two-dimensional hyperbolic tunneling, and we already can see the troubles of this direct approach along the boundary. The boundary is becoming very fuzzy. So like when we're having basically what is happens here, we have a small like fundamental piece somewhere, and it is repeating, and it consists of several splines, and these splines became smaller and smaller and smaller, and basically I run out of memory, out of computing time, whatever is a kind of limit how small I can make these pieces, and this like question how we when we stop to making these pieces when they are like small, and how to enumerate all the transformations which needed to move pieces from the center to the boundary. So another trouble of direct approach is what to do with like raster images. So there is image of some pictures from hacking, and what is the problem with like this transformation? We cannot do transform like pixels of the bitmap in direct way. If we apply transformations to the pixels of original image, they after transformation they are getting into some odd places in a destination image, not in the center of the image. And so we cannot do it as well in this direct way. But in reality, for doing bitmaps for raster images, the correct way of doing raster images, and it is doing it in opposite order. So in reality, when we are in region 1, the green one, we have to apply inverse transformation to the original image, and calculate this inverse transformation, find the color of the pixel in original image, and color the pixel in destination image by this color. And when we are in region 2, we have to do the same, but have to apply different inverse transformation to get to the source image. And in our case, all our transformations are composition of reflections. And composition of reflections, it is easy to calculate inverse of composition of reflection. It is just composition of the same reflection, but in reverse order. But I kind of did show you here. We have in this region we did have to apply one transformation, in this region to apply another transformation. But in reality, how we can find the region? Basically, it is we don't have, it is like in this case, it is I just draw like these lines by hand and to explain what is happening. But in reality, when we are doing like some drawing of the group, we don't have information about in which region we are. So we don't have information what transformation to apply. And basically, it is main problem, and the problem is resolved by very interesting and very simple. Nice thing about things when they are very simple, and called inverse pixel mapping algorithm. So for this algorithm to work, we need to choose a fundamental domain, convex fundamental domain of the symmetry group. And this convex fundamental domain is bounded by half spaces, or in case it is half splanes. And for each half space, we have notion inside and outside. And this fundamental domain has to be an intersection of inside of all half spaces. And for each size, or for each side of fundamental domain, we also attach a pairing transform, the transformation which transform the nearest to its region to inside the fundamental domain. So like we have three planes, and we have three pairing transforms, and which describe transformation of the group. And now the algorithm works the following way. So for any point in space, we start with like checking if it inside or outside of any of these sides of fundamental domain. And we if it outside of any one, so in this case, first step, it was outside of this diagonal line. We're just doing a transformation along this side, and repeat this step. So now next step is it was outside of vertical line, outside of horizontal line, outside of diagonal line, horizontal line, vertical line, diagonal line. Wow, we are got basically to the end. When we look at this sequence, it is kind of non-obvious that we will get anywhere. But nice thing that it is actually in this simple sequence on each step, we did only simple calculations. Are we outside of this plane? Apply if we are outside, apply this pairing transform, and it finally getting us to center of the to the point inside the fundamental domain, and we know how to color the original point where we started, this point 0. It is we take pixels from inside of fundamental domain. It is a little bit like history. It seems to me it is the algorithm is not quite kind of one of the troublous algorithm. I think it is not formally known that algorithm always converges. But my practice is that if you define your fundamental domain correctly, you always getting into right point. And I first learned the algorithm in its simple form from a paper of Martin von Gagern and Jürgen Richter-Gebert from 2009, hyperbolization of Euclidean ornaments. And it was used for two-dimensional hyperbolic tilings. Since that, I applied it like to 3 and 4 dimensions, and it seems to me the algorithm existed in some shape or form, like some jargon of computer programmers. Sometimes they called fold transformation, and at least in I've seen like references in different places. Oh, it is just simple set of reflection. Everybody is doing this. But reality, what we are doing, it is putting point anywhere in the space into inside the fundamental domain. And the algorithm is very robust, and it works in any number of dimensions. It is basically like I exercised it for like only up to four-dimensional hyperbolic geometry, but there is no limitation on number of dimensions to make it working. And it is particularly efficient that when it's using on GPU, every pixel is processed independently. So you simultaneously doing calculations for each pixels on your image, and it is very fast. It runs on real time, basically like 4K frame resolution takes maybe 3 milliseconds to rendering time on decent graphic card. And I show like one of the most complex things I did, animation of different rotation of four-dimensional of animation of deformation of limit set of four-dimensional hyperbolic group. And it is, I don't know, it is how good it is visible on my screen, but it is like the physical picture is here, but it is what is actually happening. It is when we start to move this image between two different fixed points. And it is another one. It is somewhat like in some orientation, it is this shape, but when it is moves in 4 dimensions or kind of rotated 4 dimensions, it takes a kind of all the different kind of variations. And it is a little bit awful example. It is 4-dimensional deformation of 4-dimensional hyperbolic group, and it kind of disturbing image, kind of from the horror movies. But it is how to get like from the pure sphere to something like that shape, or kind of a little bit like some intermediate result is here, like kind of a little bit more a fractal kind of shape. And advertising time now, it is like making all this is now part of the open source project called SymHub, Symmetry Hub, double M. Somehow somebody used SymHub with single M already for something. And if you, I can place this link into chat. Oh, I don't know where the chat is. Sorry, you can get this QR code. It is actually live, and it is can be used right now, and it runs on inside web browser, and it is even run on cell phones, but cell phones have a very small screen, and it is a joint project by me and Chaim Goodman Strauss, and with significant assistance from Scott Worthman. And now what I will show you is several applications of this SymHub. It has main applications are currently existing. It is SymPix, creating symmetric pictures, symmetric pattern from images. SymSym, it is integration of partial differential equation on orbifold and creation of symmetric animation. And SymChaos, the dynamics of iterated chaotic attractors on orbifold. And there are examples of SymPix with freeze symmetry, how you can select different images, you can select different orientations, you can choose the images, and can choose different symmetry groups. And this SymPix with wallpaper symmetries, and it is like a large set of examples, and examples are on the website, and all the interactive, you can change the pattern, you can change the orientation. It is another example with a SymPix with a triangle symmetry. It is triangle formed by 3 angles, pi over k, pi over l, and pi over m. And it is particular cases, it is hyperbolic triangle groups. And there are several of these groups. It is groups with band transformation. And now it is more a complex case. It is group with formed with a quadrilateral with KLN symmetries. and bunch of examples of these. It is now we start to apply different conformal transformation to these maps, and it can be a ring transformation, or it can be like this wedge transformation, and it can be loxodromic transformation, and it is now rational map applied to loxodromic transformation. And it is also can be bent and have like different fractal boundaries. And now SymPix with 5 splanes, it is a little bit more complex way. It is we can have like this starting from the tessellation or from symmetry, which is hyperbolic, which defined in two-dimensional hyperbolic geometry, but we can bend this. We can change its like rotation of the spheres, and it creates very interesting and non-trivial fractal pattern. And now it is in this case, it is even kind of having like these copies of hyperbolic. Sorry. Having like copies of hyperbolic plane inside, and there are several examples of these 5 planes with different conformal mapping. Another set, hyperbolic symmetric attractors. If you will start with only one attractor is implemented now, it is Clifford attractor. It is simple way of from a point we calculating using simple formula with parameters A, B, C, D. We calculate new position of the point. Where it looks nothing, very innocent, but interestingly, if we will iterate this point few million times, we will have very kind of non-trivial image on the plane, and we show like the density of points on the plane. And let's now look at this attractor. If we place with this attractor with no symmetry, if you place it close to the fundamental domain of some symmetry transformation, and now do like simple trick on each iteration, we place a point which is outside of fundamental domain. We place it inside using this inverse pixel mapping. It is not like the image now inside is not the same which was original. It's not like cutting from the original image, but now we can extend this image to the whole plane, and there is no like boundaries on this point of fundamental domain. So we started with this image inside of this rhombus, and now this rhombus seamlessly fills the whole plane. And now it is kind of when we are doing this, we basically effectively doing dynamics on orbifold. Kind of we don't have the whole plane, but have only like this surface with a like singular point called orbifold. And now it is everything you ever wanted to know about orbifold is you can find in this book by John Conway, Heidi Burgel, and Chaim Goodman Strauss. It is very nicely illustrated book. Every page has about 5 images, nicely rendered. Not like every 5 pages one image. On each page 5 images. And this cover image was made by software from SymHub. It is combination of inverse pixel mapping and conformal mapping. And there are like several of these attractors with different symmetries and different spherical symmetries, different freeze symmetries, and hyperbolic symmetries. So dynamics on orbifold is rather general idea. So we are actually doing dynamics not on the plane, but on finite size surface. And there, let's consider different systems on this orbifold. It is, for example, it can be like gray Scott reaction diffusion system or Ginzburg-Landau complex Ginzburg-Landau equation, and we can try to integrate this equation numerically sitting on this orbifold surface. And we have example of Ginzburg-Landau symmetries with different on Ginzburg-Landau with wallpaper symmetries, with hyperbolic symmetries, with different hyperbolic symmetries, and all this on the website. They are all live. Basically, you're clicking and it actually will run animation, and I will show you a couple of these animations of Ginzburg-Landau. Either you have these vortices of Ginzburg-Landau animation. They kind of behave the same time chaotical, not periodic motion, and it is doing some kind of non-trivial transformation between them. I honestly spending too much time just looking at these images, and they can be really captivating. And there are another example of it is amazing how kind of shapes transform from one shape to another shape, at the same time keeping the symmetry intact, and you don't have it is maybe kind of interesting to analyze what symmetry it is, but in reality it is for our eyes it is kind of eye candy. We can look at this indefinitely, and there are several other examples, and it is I will show you an example of animation of this common Ginzburg-Landau equation on a hyperbolic plane, and it is like these vortices. I would say there are actually two different vortices inside or inside of fundamental of orbifold on fundamental domain, but they interact with like on the surface of orbifold. They interact with copies of itself, with each other, and they doing this chaotic indefinitely dance forever. And these are examples you just run on computer and just watch it. And going to back to different equation, it is Gray Scott with wallpaper symmetries, and Gray Scott with wallpaper symmetry and conformal maps, and hyperbolic animation. And I will show you like a couple of interesting animations. Either in Gray Scott equation, it describes gliders, which are kind of these shapes can move straight lines, but when they put on the orbifold, they behave in kind of interesting way. So it is called it marching gliders. But if you will change like parameters, the shape of the orbifold, it became lame gliders. It is now crawling gliders. And now it is swimming gliders. And these shapes are pretty stable. I can disturb the shape, and it will return to this stable shape. It is like periodic solution on orbifolds, and it is kind of sneaking gliders. So kind of they are doing these small jumps, and drunk gliders. Kind of going in the right direction, but not in the straight way. And a couple of other interesting looking animated patterns. It is basically this time, I'd say it runs in real time on this application. It is basically I did recording, but they run at the same speed on in this website application. Interesting shape, which is kind of periodic behavior, but very long period. So it kind of winding in one direction and unwinding again, and start to wind in another direction, and after that changing winding direction. And it is kind of periodic behavior. It is, if I remember, it is 300,000 integration time steps between, like, over this period. So system periodic, but with a very long period. A little bit less with a shorter period, but interesting, like, shape with a spinning. At the same time, it is maybe interesting to understand what the symmetry of this. It looks like hexagonal symmetry, but in reality, it is like some 2 to x symmetry only. And it is this SimHub project. It started as a project like maybe last January to have put into open source and kind of some kind of form less experimental, which is what was before that. And there's like tons of stuff to do and directions, and it is what I want to do with this. And I guess it is possible to find a lot of different other applications. And it is, once again, it is this link, SimHub.io, GitHub.io SimHub, and this is QR code. It is what I wanted to say. Thank you for your attention.
Thank you so much. That was hypnotic at the end there.
Yeah, I'm kind of hypnotized by looking at this kind of more than I wanted to admit.
Yeah. We did hit 1 o'clock, but I'd be happy to stay on for any questions if anybody to ask a question. I could bounce one back that appeared in the chat maybe 20 minutes or so ago, although you might have answered it further down. But Madonna asked, what happens if the original image crosses the region boundaries?
It is non-trivial question, and it is solved, and you have to basically, I didn't answer it, but I would say in the application it's called draw crown. So basically you have to draw into fundamental domain, you have to draw several copies of from neighbor cells. Yeah, so it is it is it is very good question, and it can be solved in different ways, and it was solved. Yeah.
Amazing. I'll also bounce Craig Kaplan's question. Can you say something about performing geometric computations on an orbifold, comparing to like Euclidean?
I would say I'm not. Okay, yeah, it is basically it is like good simple answer. I would say I'm a physicist, so I trying to have like simple physical idea in shape. I consider like orbifold is like a surface, maybe three-dimensional surface. But to do actual calculations, you have to cut this orbifold and do special tricks to put boundary conditions on different sides of orbifold to make it to kind of to make sure that it is your calculations are continuous on both sides of these cuts. Yeah, it is the difficult question, and basically like there are several tricks of doing this, but everything, all the calculations are happening on the unfold orbifold.
Right on. Yeah, that sounds like what Craig said. Was he said, is it basically Euclidean but with funny boundary conditions?
Yes, you may say so. Yes. Yeah, it is basically like the fun is boundary conditions, and boundary conditions, they're incompatible with the grid on which you're solving, and it was kind of to obey this boundary condition, you have to do special tricks to do it. And it was done in a very simple way. It actually works with basically with almost zero computational cost.
Great. Does anyone have one more question?
I have a question. You have a, Vladimir, you have a virtual background on your Zoom. Did you create it?
Yes, it was one of my animation which I made when I first time started to. It was MC Escher animation with like this fractal bending, which creates this super fractal structure on top of the hyperbolic fractal structure, and it is on YouTube. And by the way, this image also won me like mathematical art award in 2012 or something like. It was one of the more hard thing to do to have to place this MC Escher animation, MC Escher tiling into hyperbolic animation. Yeah. Either if you do search circle limit 3 animations, you probably will get to YouTube with this video.
Fantastic. Thank you.
Thank you.
Okay, are we ready to wrap up? Any further questions? Gabe, anything else from you? Okay. Well, thank you all again for coming. Thanks for the beautiful presentations, Vladimir and Juliet and Caleb. And I'm going to stop the recording. Feel free to continue on the Discord, and we'll see you next month.